Sound is all around us. It moves through the air when we talk, through water when a whale sings, and through metal when a train rumbles down the tracks. But did you know that the speed of sound changes depending on what it's traveling through? Let's break down the science behind this. In gases, sound travels by bouncing from one molecule to another. But not all gases are equal. The speed of sound depends on temperature, density, and the type of gas molecules present. Let's take a look at how sound travels through different gases. In air at 20 degrees Celsius, sound travels at 343 meters per second. In helium, it travels much faster, at 1,000 meters per second. And in carbon dioxide, sound moves at 268 meters per second. Ever wonder why your voice sounds high-pitched after inhaling helium? That's because helium is lighter and less dense than air, allowing sound waves to travel nearly 3 times faster. On the other hand, carbon dioxide is denser than air, so sound moves through it more slowly. That's why speaking into a CO2-filled chamber makes your voice sound deeper. All right, let's talk about pitch changes. Have you ever noticed how your voice sounds different when you inhale helium? It's because helium is less dense than air, causing your vocal cords to vibrate faster and your voice pitch to increase. On the other hand, inhaling carbon dioxide, which is denser than air, slows down the vibration of your vocal cords, lowering your voice pitch. It's a fascinating demonstration of how the medium through which sound travels can affect its properties. So, how does sound travel in liquids? Well, unlike in gases, the molecules in liquids are more closely packed together. This means that sound waves can move through liquids more efficiently and generally at a faster speed. The closer the molecules, the quicker the sound can be transmitted from one molecule to the next. Now let's dive into liquids. Unlike gases, liquids have more tightly packed molecules, making sound travel much faster. But the exact speed depends on how the molecules interact. For example, sound travels faster in water than in oil because water molecules are more tightly bonded. It's these interactions that determine the speed and efficiency of sound transmission in various liquids. Let's take a look at how sound travels through different liquids. In water at 25 degrees Celsius, sound travels at 1,480 meters per second. In seawater, it speeds up to 1,530 meters per second. And in oil, it moves at about 1,400 meters per second. In fresh water, sound moves at almost 1,500 meters per second, 4 times faster than in air. That's why dolphins and whales use sound waves for long-distance communication underwater. Salt water is even denser than fresh water, so sound moves even faster. This is why sonar technology works so well for submarines and deep-sea exploration. Oil, being more viscous, has a slightly different sound speed, but it still allows sound waves to travel far faster than in air. A real-world example, an ultrasound machine using sound waves to image inside the human body. In solids, sound waves travel incredibly fast, much faster than in liquids or gases. This is because the molecules in a solid are tightly packed together, allowing the waves to move quickly from one molecule to the next. Now for the fastest medium, solids, because their molecules are packed even tighter, sound moves incredibly fast. Solid speed of sound, mess wood. 3,300 meters per second glass, 4,540 meters per second steel, 5,960 meters per second. Ever noticed how knocking on wood produces a sharp, fast sound? That's because sound moves through it 10 times faster than through air. Glass is even better at transmitting sound, which is why it's often used in musical instruments like wine glasses that sing when you run a finger around the rim. And here's the champion, steel. Sound zips through steel at nearly 6,000 meters per second. That's why railway workers used to place their ears on train tracks to detect incoming trains long before they could hear them in the air. A person tapping a metal rod and hearing the vibration instantly at the other end. Let's put everything into perspective with this ultimate speed comparison. All right, now let's take a look at a comparison chart summarizing the speeds of sound in different mediums. In air, The speed of sound is 343 meters per second. In water, it's 1,480 meters per second, and in steel it reaches a whopping 5,960 meters per second. As you can see, sound is fastest in solids, slower in liquids, and slowest in gases. But why does this matter? From music production to deep-sea exploration, understanding how sound moves helps us design better technology and improve communication systems. Whether it's the deep hum of a whale call or the sharp clang of metal, the speed of sound is always changing based on its medium. Now, the next time you hear an echo or talk underwater, you'll know exactly why it sounds different. Whether it's the deep hum of a whale call or the sharp clang of metal, the speed of sound is always changing based on its medium. Now, the next time you hear an echo or talk underwater, you'll know exactly why it sounds different. Enjoyed this deep dive into sound physics? Hit that like button and subscribe for more science content, and tell us in the comments what's the strangest place you've ever heard sound travel. See you next time!